Okay, let's begin. You know something? I can't touch you without you touching me. I can't push on you without you pushing on me. I can't nudge you without you nudging me. I can't interact with you without you interacting with me. And this brings up a law of physics, gang, and what's the name of it? Newton's what? Newton's third law, the law of action and reaction. I can demonstrate that like this. I'm bending my fingers up the most I possibly can. That's the most I can bend my fingers up. I can't bend them any higher. But if I push them, I can. Let's suppose I push on the podium. Now my fingers are being bent up. What's bending my fingers up? Yeah. That's the most I can bend them. Would you push on my fingers, please? Now my fingers are bent just like before. Okay? What's happening to my fingers, gang? They're being pushed on, isn't that right? They're being pushed on. That's why you see them bent up like that, right? How about when I touch the wall over here? Was the wall pushing on my fingers too? See, a lot of people don't see that. Non-physics types don't see that. But physics types see, hey man, he's pushing on the wall. And what's the wall doing to him? Watch how I lean. I'm leaning on the wall, huh? Okay? Now, everybody say, hey, the dude's pushing against the wall. Okay? Call this the wall. Okay? Everybody sees the dude pushing against the wall. Physics types see that too. And physics types see something else. And what else do physics types see? Check your neighbor, see if you're sitting next to a physics type. So what's happening, gang? When I push on the wall, what's the wall do? Hey, you know something? I can't push against that wall without the wall pushing on me. And this further defines an idea we've been talking about all this time. And that's the idea of force. When you impress a force on something, you tend to accelerate that something. That force we're going to further define. A force is an interaction between one thing and another always, all the time. A force is an interaction between, in this case, my hand on the wall, if this is a wall, and what's the reaction? That'd be the action force, hand on wall. What's the reaction, gang? Wall on hand. You can't push on something without being pushed back. Can't be done. Here's a couple of blocks. These blocks right now don't interact with one another. But now I'm going to attach them with an elastic band. So the big block, when I stretch it, will pull on the little block. Okay? Now, which block is pulling? Is the big block pulling on the little block? Or is the little block pulling on the big block? What do you suppose? Check your neighbor. Now watch the blocks. I'm going to let the blocks go. And sure enough, did you see them both move? That's strange. The more massive block didn't move as much as the little block. I wonder why. Maybe the pulls were different. Maybe the big block is pulling harder on the little block because it didn't move very much. Why don't we make the mass of the little block even more? And what I'll do is I'll put some clay on it, okay? Make it more massive, okay? Now, will a little block pull harder? And we see they both move about the same. If they did move about the same, what could you say about the forces that act out in each? And what can you say about the masses of each? Yeah. Now, when I make them unequal masses, and I pull, which pulled harder? The big one on the little one, or the little one on the big one? That's a question for you to think about, and check that with your neighbor right now. How many say they might be different masses, but you know what? They're both pulling on each other the same. Show of hands. Is my people, my people. All right, all right. Well, let's test that. Could you do something for me, please? Could you hold this rock? We're going to have a tug of war here. Okay, Helen's going to pull the rope that way, and I'm going to pull it this way. Now, who's bigger, me or Helen?
Helen.
Yeah. Okay. Now we pull. Okay. Now, who's pulling harder? Am I pulling her harder, or is she pulling me harder? How are we pulling, gang? How? Check the neighbor on that one. What do you suppose? Is she pulling me harder, or am I pulling her harder? Huh? Who's pulling harder? Is that so? You used to say, I'm pulling harder because you see the rope moving this way. That's what you used to say. Remember the old days? when you didn't have that spark called what? Begin with a F. Physics, all right? And now you're getting that spark, right? And now you're starting to see the world a little differently. Let's try this with a couple of scales. I'm going to attach this right on here. Okay. Now you pull that side, and we can measure the force, gang, yeah? And I'll pull over here. Now you look to see who pulls harder, me on Helen or Helen on me. And here we go. How do the readings look, gang? Huh? Which one's harder? How about there? How about there? And what are they, gang? SS. Same, same. I can't pull on you any harder than you pull on me, okay? And when I touch you, who's touching who? Am I touching her or is she touching me? She's touching my hand. I felt it. From my point of view, she's touching me. From her point of view, I'm touching her. Who's touching who? We're touching each other. Thank you, Helen. My thumb, my forefinger. They're pulling on each other. Which is pulling harder? The thumb on the finger or the finger on the thumb? Check your neighbor. Now I got another question for you, gang. A question maybe you couldn't answer a year ago, and a question today you can answer. And you check this when you go home. Check the folks at home and ask the folks this. Hey, is the Earth pulling on the moon? They'll say, yeah, it's kind of pulling the moon around in orbit. Okay. Say, but if you lived on the moon, would you say that the moon is pulling on the Earth? Now, that moon's kind of small compared to the Earth, only 1/6 the mass. And what would your parents say? Is the moon pulling on the Earth? What would they say? Let's suppose they say, yes, I think so. Now you say, hey, which pulls with the greatest force? The moon, the Earth pulling on the moon? Or the moon pulling on the Earth? Remember when you weren't so sure about a question like that? What if I'd asked you guys that question a month ago? What would you have said? Man, that's a big moon. That's a big Earth, honey. That's a little dinky moon. That gravity of that Earth, honey, pulling that moon right down, right? Well, maybe the moon pulling a little bit back, but how hard back? Check your neighbor now. E. Which pulls harder? You learning this stuff? Huh? Is it kind of fitting? Huh? The moon and the Earth are pulling on each other in one interaction. And that one interaction is Earth pull on moon, moon pull on... You can't have one without the other. They're both counterparts of the same interaction. Do you see that? We can put that down as a rule. If body A pulls on body B, call that action. Then reaction is body B pulls on body A. It's that simple. Let's put that up here. If action is A pulls on B, A could be the Earth. The Earth pulls on the moon. How can that be? Unless A, okay? And we call that the reaction. Reaction is just whoop, switch them around. B pulls on A. It's that simple. You got it? I want to move across the floor. What I do is I push back on the floor. I push back on the floor with my feet. I'm pushing the floor this way. If I were on a skateboard, you'd see it move that way. Huh? I push back on the floor. What pushes on me? The floor. If I push back on the floor, honey, the other part of the interaction is the floor push on. That's why I move. You're in the swimming pool. You're here. You want to get there. What do you do? What do you do to the water? You push the water back. When you push the water back, how can you do that without the water pushing you forward? So you push the water back, the water pushes you forward, and away you go. You want to learn how to swim fast? Push as much water back with as much speed as you can. And the more water you push back, the more you push on the water, the more the water is going to push on you. And that's what makes you move. You see a car going down the street, huh? Now you're all sad. You see a car, you see the cars going down the road. Give some respect to the road. Because what's happening? The wheels are turning, huh? The wheels are turning. Are the wheels pushing against the road? And which way are they pushing against the road right here? This way, right? So the wheels are pushing the road that way. That's the road. Now, what does the road do to the wheels? The road pushes the wheels this way. And the wheels are connected to the car. And so the car then moves. That's why. Try this with your friends. You're out there looking at the cars go by in the road, right? You say to your friends, wow, man, look at that road pushing those cars along. True or false? True or false? The road pushes the cars along. Come on. Hey, you believe that? How many say, sounds right to me? Boom. Show of hands. How many say, no way, man. I can understand the wheels pushing on the road, but it stops there. That road don't do any pushing because the road ain't alive. You got to be alive to push. Is that true? Huh? When I was pulling this scale over here, you saw this thing read some readings, and you saw Helen's hand on the other side. Let's suppose from Helen's hand, I put it on a hook on the wall. And now I pull. Couldn't I get the same reading? What's holding it? The wall's dead. How can a dead wall hold? The dead wall not only holds it, it pulls it just as if a hand were there. You can't tell the difference. If you're doing a tug of war, you're playing a tug of war with a whole lot of people. Get a whole, these people here, huh? You guys all pull a rope, huh? And you guys pull the other side, yeah? And you pull it, both pulling, huh? And what's the tension say there if these people here pull with 100? What do they have? And it stays still. What are these guys got to be holding it with? What's the reading on the scale? 100. Now what I do is I take a break, and I take a curtain. I put a curtain here, and I cut a hole through it, and I put the rope through it. I say, okay, we're going to do it again, gang. We're going to do it again, gang. Hey, we're going to play a trick. You guys sit down. I take the rope, and I put it on a hook on the wall. Hooked on there, right? I say, okay, pull like before. These guys over here, they pull just like before. They're pulling with 100, right? What's the scale reading say here? 100. Yeah, some people say 200. What do we say? 100. Okay, okay. 100. What's going on the other side? That's right. The wall's pulling. It's just as hard as the rope pulling on the wall. This is stuff hard. This stuff is kind of neat, ain't it? Huh? You can't have a force without a counterpart. You can't have something pulling on something. Ain't that nice? So the wall pulls just as much as a human being. Same thing. Question?
What's the tension?
The tension would be the force that tends to stretch it. See, and that tension would be the same all throughout the rope. Even if the rope moves like this, see, it'd still be more. It turns out in a tug of war, the person to win in a tug of war is not the one that pulls hardest on the rope, because the rope may be pulled on both sides equally all the time. It's the one who pushes harder against the ground. The one who pushes against the ground harder, see, because the rope's a standoff. The four ropes can't cancel out. So if I push against the ground the harder than she pushes against the ground, then I'll pull her and I'll win the tug of war. So how could you play a tug of war on ice with slippery, slippery feet? You'd pull on the rope, and what would you guys do? You'd pull toward each other. So no one would go the other way. Can I see that? See? You're riding your bike. You don't have a 10-speed. You can't afford a 10-speed, honey. You got a 1-speed. And you're going up a road, and the road's like this. Now you got to pump. You got to go up the road. What do you guys do? How many people sit on a seat and try to pump and going up? You don't do that. You stand up, don't you? And when you stand up, don't you pull up on the handlebars when you push down? Why do you do that? Why? You all do that. You pull up on the handlebar and you push down on the pedal. And then you go pull up. You're all the time pulling up on those handlebars. What are you pulling up on the handlebar for? Why? When you pull up on the handlebar, against what? Against the pedal. And that makes you move better. Ain't that neat? Yeah. It's like this too. I remember when I was a teenager, man, I was really, really skinny. All my friends weighed more than 100 pounds. All my friends weighed more than 100. I was in the 90s. And about as tall as I am now. Like a toothpick, man. And I remember, this is Scout's Honor. I remember I used to go into the drugstore. And I'd drink milkshakes, I'd do everything I could, you know. And everyone said, how come you're not gaining weight here? I'm trying, like, okay, couldn't do it. And I would go into the drugstore, and I would get on a scale and make sure none of my friends are around, and put the penny in. Oh, 94. Will the day ever come? Will the day ever come? Okay? Well, one time I'm over at a friend's house, and my friend had a bathroom scale in the bathroom. And I walks in the bathroom, looks to make sure no one looks. I'm always afraid someone's going to come by and say, "Hey, Hewitt, you don't even weigh 100. Hey, everybody, you know what? Hewitt here don't weigh 100 yet." I was afraid of that, you know? Okay. Anyway, one day I'm at a friend's house in the bathroom. He's got a scale. I look, there's no one coming. I step on the scale, and there it is, 94, right? And the friend walks in. And I grab the sink. I grabbed the sink, gang. I grabbed the sink and I pulled up on the sink. When I pull up on the sink, finish it up, come on, come on, come on. What happens? The sink pushed down on me, whip boom, 103 digits. I'm there, okay? Some people get the opposite problem, okay? They weigh too much. They're a little bit maybe self-conscious about the weight. They walk in. There's the sink. The sink's still there, yeah? They walk in. Oh, there it is, a 300. If only they weighed like only 290, right? But 300, and they're feeling self-conscious. What's wrong with a 300? There's 300 pound types. It's 99 pound types. It's okay. It's one world, ain't it? But still, you get a little hung up because you want to be like the norm, right? Now, you're a 300-pound type. You walk in, and your friends come in, and they're just going to look and see the 300. There's the sink. Tell your neighbor what you would do. When you push down on the sink, honey, finish it up. Sink push up on you, make you lighter against the scale, and you get a lower reading. Okay, you can step on like, look, I'll be 0, okay? You can do it. Newton's third law. Newton's third law is not so easy for a lot of people. In fact, back at City College, when we used to hire teachers, we would have students come in and let the teachers perform and do a 10-minute gig on the blackboard. And we'd always have a student ask the following question. Because we wanted to ask a question which sounded very easy, but wasn't. Like if you asked a teacher, like, what's the wavelength of the Baumol line for the hydrogen transition? He could say, oh, I see, it's a trick. And he'd say, well, I don't know the answer to that, but I'll look it up and I'll tell you next time. Because that's the kind of question that you know darn well you're not supposed to know the answer to, right? But we wanted to ask the prospective instructors a question for which they thought they ought to know the answer, like an easy question. And we found a very, very easy question that not many people could answer. And the reason they couldn't answer is because they didn't have the framework that you guys have right now. And it's this. First of all, we didn't word the question very nicely. We'd have the student say, hey, when I take an object and I drop it, it falls. There's a force on it, right? The instructor said, yes, that force is called the force of gravity. What's the reaction to that force, teach? Anyone want a job at City College? See if there's anyone in this class who can answer that question. Here it is again. I let go of the play. There's a force acting on it. You saw evidence of that force because you saw it accelerate. Here's your question. If there's a force acting on that, what's the reaction force? E. Talk it up. Anyone sitting next to someone ain't saying anything today? If so, put your hand up and go like this. This person ain't talking to me today, honey. Is that right? Is that right? Okay. Hey, what's the does anyone happen to know the answer? What's the reaction to the force of gravity acting pulling down on this? Someone want to try it? Lee?
The ball is pulling the earth up.
Right on. Lee, you got a job at City College, huh? You get through here and get your blah, 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 okay? That's right. Let's suppose I had asked a question like this. When I drop this, the earth pulls downward on the clay. If I phrased it like that, the earth pulls downward on the clay. What's the reaction? If you would ask that to a teacher type, the teacher type would say, earth pulls downward on clay. The reaction is the, check, see if your neighbor knows. Come on, come on. You see, you guys could answer the question this time because the question was phrased properly. It's how a question is phrased that depends a lot on what kind of answer you're going to get. That's like the monks who were smoking in the monastery. Not supposed to smoke in the monastery, especially in the prayer room, okay? And so one monk sends a letter to the high bishop and says, is it okay to smoke in the, is it okay to smoke while we're praying? And the high bishop could only say what? No, you can't smoke while you're praying. That's a sacrilege. No smoking. And the other monk sends a letter and says, is it okay to pray while I'm smoking? Yes, you can pray anytime. Okay. Do you see what I'm saying? How you phrase the question depends a lot on what kind of answer you're going to get. Okay? So again, if I say the earth pulls down on this, what's this pulling? And then as Lee stated, the clay is pulling up on the earth. But you see, just asking the question, there's a force on this, what's the reaction force? The question is not phrased so well. Do you see the difference? Oftentimes when you can't answer questions, it's because the questions themselves aren't clear. When the question's clear, and you kind of know your stuff, then you can kind of pick it up and answer it, yeah? You know, when I drop this, it's quite evident the force is acting in this, because the acceleration is noticeable to us all. Is there really a force pulling upward on the earth? I tell you what, I'm going to do it again. No, not check your neighbor. I'm going to ask you to be very, very quiet. Notice that the chair is pushing up on you right now. Can you feel the chair pushing up? And you're pushing down, and it's even Steven, so we're all at rest. But nevertheless, the chair's pushing up, right? I'm going to drop this and see if you don't feel all of a sudden the chair rush up against you a little bit. Try it. How many felt it? You didn't feel it. You know why you didn't feel it? Because the mass of this thing is tiny, tiny. Look, here's the idea. Here's the force that pulls this down. Huh? And here's the force that pulls the earth up. But how about the accelerations of both? The acceleration of this is simply that force divided by its mass. And that turned out to be 10 meters per second per second. We talked about this before. But how about the force that acts on the earth? The mass of the earth is like this. And when you take that force acting in a humongous mass, you get an acceleration like this. See it? It's like negligible. And so you don't sense it. But if the earth were smaller, and this were more massive, in fact, what if this were as massive as the whole world? And we held it like this and we dropped it. How far would it go, gang? Would it go all the way down there?
Halfway.
It would go halfway. That's right, because if this was as massive as the whole world, then this would come down just as much as the earth would come up, and it'd meet halfway. Ain't that neat? Ain't that neat? So you can take ideas and stretch them, stretch them, stretch them, and they become fascinating. I take a rifle. I fire a rifle. Blam! Any force act on a bullet? Oh, yeah, honey. You know darn well the force acting on a bullet. That bullet accelerates. Humongous acceleration. So you know there's a force on the bullet. Any force kicking back on the gun? Let me ask you a question. Can there be a force on the bullet? Can the gun exert a force on the bullet without the bullet exerting a force back on the gun? Can it? No! There's an interaction between the gun and the bullet. So gun pushes on bullet, bullet pushes on. That's the recoil. You fire a rifle, boom, it comes back against your shoulder with a force. How big is that force compared to the force that pushes on a bullet? Same. What would you guys have said about a month ago? Oh, only a little dinky force on the gun, honey. A humongous force on the bullet. Ain't that right? But you don't say that anymore. You know why you don't say that anymore? Because you got physics. Because you learn in physics. You learn this stuff. You're learning, huh? You're learning the physics, yeah. The forces are equal and opposite. But you know what? The effects aren't. The effects of the force are different. But the forces are the same. You know what this means now? Critical thinking. You have to distinguish between a thing and its effect. Dumb people can't do that. And they get in trouble. We Can or can't? We're going to be seeing, okay? Let's look at this. And you fire a rifle. Here's the bullet. Bullet races out. And the bullet has a force acting on it. But that gun kicks back. How much force? Really the same? The same. The same force acting back. Now, the acceleration of the bullet, a lot or a little? The answer begins with an L. A lot. Because here's the mass of the bullet. Here's the mass of the rifle. So here's the acceleration of the bullet. Boom! But here's the acceleration of the rifle. So the rifle only goes back to here. In the same time, the bullet goes from here to here. That bullet is accelerating like bonkers, right? Inside the barrel. Now, when it gets outside, is it still accelerating? No. Now it coasts. We talked about this before. It's accelerating down. That's why it drops. So it follows the curved path. But while it's inside, the forces are the same, but the masses are different. That means that the effects are going to be different. What do you mean the effect? How much it moves. You see? So the big thing only moves a little bit. The little thing moves a lot. And they got the same force. That's the two blocks that I pulled before. I pulled the massive block and the light block. And they pulled toward each other. But the light block moved a lot. Some people say, oh, there's more force on the light one. And you guys say, same force, less mass, more acceleration. Now you got to tie all those ideas together. Force, mass, acceleration. How many people do you know that are good at thinking about three ideas at one time? You hear people say that physics is a tough subject. You know why? Because you got to think of multiple ideas at once. Well, maybe not at once, but you got to consider multiple ideas when you're asked a question. And whenever I ask you any question about acceleration, there's two ideas you're going to consider. Two! You know what your friends out in the street are going to consider, how hard it's pushed or pulled. But you guys are going to consider not only how hard it's pushed or pulled, but what else? How much mass you got, honey. How much mass is being pushed or pulled. And when you consider that also, now you've got it together. And that's Newton's second law. Okay. And this force here is part of some interaction. Here's the other part. Newton's third law. E. Newton's first law, the idea of mass to begin with, huh? Things have mass, they have a tendency to remain at rest. That rifle has a lot more tendency to remain at rest than a little slug of bullet. Okay, so the masses are different, but the forces are the same. That's today's lesson. And the accelerations are different. That's last time's lesson. Do you see how all those ideas connect? It's the connection of ideas. So you're traveling in the wrong country at the wrong time, and it's totalitarian, and what they do is they capture you, and they say, hey, we got you, honey, up against the wall. And they put you up against the wall, they handcuff you. You look at the wall, you see all these bullet holes in the wall. You say, oh, no. And they put you up against the wall, and some guy comes out with a great big high-powered rifle, and he's got these little eagles over here, and he's got a cap with eagles. You know, eagles are strength or something, okay? And he's polishing his rifle up. He's just going to aim it at you and do you in. And you kind of look at him, and you kind of give him some obscenities, okay? And he says, oh, hey, wait a minute. He says, we're not barbarians here. He says, I'll at least give you one last wish. And you say, one last wish? He says, yeah, one last wish. Here's what you might wish. You could say, okay, I'm guilty of whatever it is, even more than you say. And what I want you to do, I'm not trying to be a wimp out of it. I'm not going to wimp my way out. I want you to shoot me, okay? But I don't want you to shoot me with that little dinky bullet. I want you to shoot me with a humongous bullet. More humongous than a rifle from which it's fired. And I want you to pull a trigger. What's going to happen? Who's better off, the target or the shooter? What's going to happen to that guy when he fires? We're going to walk around the rest of his life like this. One of his eagles gone, right? Rockets. First day I was here talking to you guys, I said, how does a rocket move? And remember, we all get in the swimming pool together? And we get in the pool, and I pushed against the edge of the pool, and I rocketed across the pool, right? And I said, is that how a rocket works? And you guys said, yep, sure is, Hewitt, sure is. And I said, nope, it ain't. And you says, oh, wait a minute, what's going on? Let's talk about that now. How does a rocket move? What makes a rocket go to the moon? Does it push against the launching pad so hard that it bounces up and just keep going, 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 like throwing a super ball against a ground and have it bounce to the moon? Is that how a rocket works? What pushes on a rocket, gang? Like this gun. That gun's being pushed the opposite to the direction the bullet's going, yeah? If I took that gun and I held it down like this, and I fired it, would the gun kick up? And after it fires one bullet, it fired another, would it go kick, kick? Would it kick twice? Let's suppose I have a machine gun, Hank, and I put that machine gun on like a piece of piano wire. See the piano wire stretched tight here? See? See, it's nice and tight, okay? Twang. Now I put that machine gun on a couple of screw eyes, okay? And I take the machine gun and I pull the trigger. Brrr! What's going to happen to the machine gun? Can you guys see it climbing up? It's going to recoil away from the bullets it fires. The gun pushes the bullet down. The bullet pushes the gun up. Now a rocket fires bullets too. Made out of lead? No, molecules of gas. Fires them fast or slow? With a lot of force or little force? A lot of force. So those gas particles are fired out. They're pushed out, right? So the rocket pushes the gas down. You guys can finish it up. You know how a rocket gets to the moon. See, people used to think that the rocket pushes against the air. In fact, the father of rocketry, Robert Goddard, said back in the 20s, hey gang, the time is coming when the human race will get to the moon with rockets. Not airplanes, rockets. And he was belittled and he was humiliated by the press. And one press person says, Dr. Goddard obviously doesn't know his science. Because if he studies books, he'll find out that between here and the moon is a vacuum. And there's no air for the rocket to push against. So a rocket could never travel in a vacuum. And that's what they said. What do you guys think about that? Can a rocket travel in a vacuum? You know a rocket can travel in a vacuum because this is what? This is almost the year 2000. So it's the times. But back then, 80 years ago, 70, 80 years ago, people didn't know about these things so much. It wasn't part of the general consciousness. In fact, Goddard did this for the press. He did the following experiment. He put a pistol inside a vacuum chamber. And he pulled a vacuum. So there's no air in there. Drop a little feather, boom, fall just as fast as anything else. A vacuum in there. Then what he did is he had a little mechanism whereby he could pull a little trigger outside, a little stick would come up and pull the trigger of the gun, and he showed that when the bullet went down, the gun went, and he says that's how a rocket works. The bullet doesn't need any air to push against to make the gun go back up. It's straight Newtonian physics. Rocket pushes down on gas. Gas pushes up on rocket. Phew, there you are, and you can go all the way to the moon if you keep pushing. A little story goes with that. Human beings went to the moon, 1969. Before 1969, they were talking about going to the moon. My brother had a dear friend, Perry Hunter, sort of like a scientific type guy. And Perry Hunter and my brother used to get in arguments about this whole Apollo mission as to whether or not humans could get to the moon. And I remember one time overhearing an argument between my brother Dave and Perry Hunter. And Perry Hunter was claiming, no way a human being's going to get in a rocket and get to the moon and come back. No way. It's all press. It's all a farce. It's all Hollywood. They can't do that. And my brother says, Perry, how do you know they can't do that? And Perry said, because I'm a marksman. And I know what it is to take a rifle and get 200 yards away from a target and boom, hit that target dead on. I know what that is. And when you talk about going 240,000 miles away, I don't care what kind of high tech they got. They're not going to aim that rocket properly. They're going to miss. Perry didn't understand at all how it happens. Gang, they don't aim a rocket to the moon and fire and hope they aimed it right and it hits. That's not the way it happens. How does a rocket go to the moon? They could never do that without high-speed computers. They fire the rocket in the general direction of the moon. Now, as the rocket's going out, the rocket sights on the stars, sights on the moon, sights around, and answers the following question. Where am I? The rocket can ask that question and answer it. Then the rocket says, What's the best way from here to the moon from where I am? Not where I was. From where I am, what's the best path? That path is calculated. Little rock, push it on that particular course. Then I go, a little while later, boom, rock, where am I? Okay, what's the best possible way to get to the moon given where I am? Then plots a whole new path. It isn't like there's one path and if it gets off the course it tries to get back on. It doesn't do that. It plots a new path all the time. Keep getting closer and closer and closer, plot new paths and follow those new paths. Whip, boom, bullseye. That's how they do it. So if you're ever in life going from one place to another, you say, I want to go to here. You get off the path. You don't have to get back on the path. What do? You say, hey, what's the path, the best path from where I am, not where I was back there when I was 16 or 17 or 18 or wherever like that. So you go by steps. You plot a new path all the time. You take a piece of paper. The piece of paper, you say to the heavyweight champion of the world, hey, champ, do me something, I give you $1 million. You say, what? Hit this piece of paper with 50 pounds of force. Is he going to collect $1 million? Get the heavyweight champ of the world to throw his best right hand. Whoa. Hit that paper. Hit that paper with 50 pounds of force. Get $1 million. Can he do it? Can he? Can it be done? No. You can't hit that paper with 50 pounds of force. You know why? You can't get that kind of interaction with that little dinky piece of paper. You can't get it. This paper is not capable of giving you a 50-pound interaction. You can't hit this paper any harder than the paper hit back on you. So you can't do it. That's what Gandhi was talking about. You can't be pushed any harder than you push back. Can't do it. Now take the paper and hold it against the wall. Boom. Can you get 50 pounds on the paper? Oh, yeah, you can get 50 pounds on the paper, okay? Because what are you doing? You're pushing against the wall now. And the wall can push back with you 50 and squash the paper and it'd be 50, huh? But just on itself, you can't do it. Ain't that neat? So what are we illustrating here? You can't exert a force on something else unless that force exerts the same amount back on you. Ain't that neat? That's Newton's third law, gang. Yay. You got it? Here's a horse pulling a cart. And on the cart is a farmer over here. Okay? The farmer's yelling at the horse. And this cart's all loaded up with bags of bananas or something the farmer's going to bring to town, okay? And now, what the farmer says to the horse is, horse, pull the cart, I want to go to town. And the horse says, wait a minute. No sense me pulling on the cart. Because if I pull on the cart's going to pull on me. And if I pull hard, the cart will pull back hard. And however hard a force I exert over here, there'll be an equal and opposite force pulling back this way. The forces will cancel out. So we might as well just stay here. The farmer says, no, pull, pull, pull. I guarantee if you pull, we'll go to town. And the horse says, but I don't see it. Every action, there's a reaction. How are we going to get to town? How does the system move, gang? It's true that for every action, there's an opposite and equal reaction. Why don't they cancel out and nothing happens? Think about that. It'll make for a good weekend. All right? Okay, physics.